Okay, my outstanding friends, they are making some claims here about light and the first time ever that it's been photographed as a particle, etc. Well, I don't really see that, but we'll go through that. But at the same time, they say 2015 this picture was taken. Well, we had photoed photons, muons, electron neutrinos, the whole 9 yards by that time. But let's see what they have to say, and then I will show you what we did.
Looking at the first ever photograph of light as both a particle and wave captured in 2015. But you need a source of light to take a photo, so how do you take a photo of light itself? Researchers figured out a clever way to do it. First, they fired laser light at a tiny metal wire. This trapped the waves of light on the wire. Then they fired a stream of electrons alongside the wire. The light waves on the wire are made of particles called photons, so the electrons bounced off the photons, causing some electrons to speed up and some to slow down. The changes in speed show up as energy packets or quanta that can be visualized. They put the wire under an electron microscope and snapped a photo of it. The top part of the image is the standing wave, while the bottom shows where the photons are located. This experiment demonstrated that we can film quantum mechanics and its paradoxical nature directly.
Okay, so they claim that this is the first ever captured in 2015 particle and a wave. Now let's watch what they have to say, and then I'm going to show you our research in relation to theirs.
In 2015, but you need a source of light to take a photo, so how do you take a photo of light itself?
Very simple. Here's how you do it. Okay, I'm going to show you exactly how you photograph light, and you use CMOS. And guess who else is going to start using it? MU, this is the muon 3E, Alice, Star, Bell upgrades. All these are going to be upgrades to use CMOS. CMOS is really getting somewhere, in particular in terms of radiation hardness. Now that's the only problem, is when you really radiate the hell out of something, you just burn it up. So they're working on hardening the CMOS capability of taking on these really intense energetic particles. Well, they've already done this with the cell phones, smartphones. Back in 2015, when we did this, they claimed to have just seen these in 2015 as well. We actually photographed them. But see, they don't even really know much about CMOS yet, because they were using other really fancy detectors. So they're trying to implement the CMOS in with that and sort of continue on what they're doing, but add the CMOS. Well, they don't need to continue on what they're doing. They just do it with the CMOS. A smartphone. Literally, I'm not kidding you. Okay, just so you understand, the CMOS is what everything works on, and it was working on it back in 2014, 2013, somewhere in that area. Same time I was trying to communicate with Fermilab. And I said, this is how we're doing it. We're finding muons. When a muon strikes the semiconductor, which is the CMOS, that underpins a smartphone camera, it liberates an electric charge. That's from the luminosity. Creates a signature in a pixel that can be logged, stored, and analyzed. Exactly what we did. Cosmic rays emanate from far beyond our solar system and are constantly bombarding our planet. Well, the reason that they're seeing them way out as they hit our atmosphere is because they are concussing just like a particle collider. However, we don't have to do that. We can do it with light here using a field crusher instead of a head-on collider. We have everything going right down into a field, and the fields can't get away from each other, so they crush. And then the black particles come down and just smash them through like a jackhammer. That's what's causing them to squirt through there so violently. Okay, so how do you photograph light? Well, now they're exploring new experiment at the high luminosity LHC. Well, this is brand new, high luminosity. What's luminosity? It's glow, luminous, glow. What happens? CMOS picks up the glow. You don't need all this other equipment they had. And they're trying to still continue to use it. They don't need it. The high luminosity upgrade, $950 million worth of magnets to the Large Hadron Collider scheduled to begin colliding protons 2026. We could do it right now with light, which is what they wanted to do 50 years ago. This major improvement to CERN's flagship accelerator increased the total number of collisions in the experiment by a factor of 10. All right, so now they're going to do all kinds of special stuff to cope with all this extra energy. Well, let's take this a little deeper, because we can do this right now. We don't need any of the stuff they have, none of it. It's totally unnecessary. See, this is what they're talking about at CERN, high luminosity upgrade. Major upgrade. LHC collides tiny particles, which are protons. We collide light, which is much tinier, 1,836 times smaller. Now, so they're showing this high luminosity. What is luminosity? Luminosity, the measure of the number of potential collisions given in a period of time, is an essential indicator of an accelerator's performance. The number of collisions over a certain area in a certain period of time, accelerator's performance. That is how they tell how well they're working. Let's see if we can see one that's working real well. Okay, my friends, this is from our actual research, and they want to know how can you photograph light. You use CMOS because it picks up luminosity. This is luminosity. Now, let's start right from the very beginning. They say a particle and a wave. Well, let's look at the wave. All right, here's the wave. Now, you can see that's a wave, quite obviously. And that is light, and we're using CMOS, just a smartphone. This is very well understood. The CMOS picks up luminosity. This is very luminous now because it's beginning to accelerate. All of these little dots are gases and particles that are in the air that also have a magnetic field surrounding them. There's a particle right here in the center that's coming through the air real fast, and it has a glowy little spot on the bottom, which I will show you in a second, and that concusses all of the things that are in front of it, and as it fills up its charge, it flops, and then this one that was real charged goes to the back. This one goes in the front and gets a charge. When it gets overcharged, it flops, and then it starts all over. So it spins. Light spins through the air. Charge, discharge, charge, discharge, charge, discharge. That's what's going on here, which creates this magnetic field. That's the field. Anytime you have a charged particle spinning, there's a field around it. That's a fact. That's what happens with a motor. Creates a field because there's a charged particle spinning. Now, so what we have is the wave. And what we had back here was the particle. Can I show that? Yes, I absolutely can. And I will show this light accelerating, which is not supposed to happen. So let's take a look at that. All right, so don't forget, this right here was the particle, it was the wave, and the particle I told you is in that wave, creating the field. Now here is that wave accelerating. I don't think anybody could possibly deny that understands acceleration. I mean, now plus, you see that little white zzz? That is literally the particle. That is the particle. That is a photon. Now, another thing I want you to see is, while we're here, is look at this reverse radiation. Do you see that? That is a reverse, and that's because of this concussion zone here, which, you see this luminosity? That is what they said shows the performance of a particle accelerator. You don't see any more luminosity than that. You can't get any more luminous than that. This is 100% white, and I will show you the black particle that is attached to the white is gone now. It can't get through this venturi, and then it reattaches out here. So we have fission, we have fusion, which creates scads of luminosity, which luminosity is energy. Energy is power. We have increased the power of this wave exponentially, I think. You make your own determination. But don't forget, this wave right here is where a particle is coming. There's all kinds of particles coming here, but you don't see them doing this, because this one here is directly in line with the Venturi. That's the only reason you're seeing this one. These are all out here, the same as this. They're all over here. The only way we're seeing them now is because of the reverse concussion. We're seeing this one because of it's being pulled forward. We're seeing these because they're being pushed backwards. They're smashing into a wall of reverse particles. And this is where the particle separation occurs. So from here to here, we have what's called a tau particle. And I will show you this in a second. From here, as you see it glow, we have photons. From here, we have a split. We have sterile muons, which is the black, and we have the white electron showers. Here, we create the Higgs fields, which brings back the black and the white together. And I will show you all this. There's a new electronic model, a nuclear model, which says in the subatomic range, well, everything is dipoles. There is nothing but dipoles. Electrons are not negative. They're a positive and a negative, and they're dark matter, and they're glowing matter. Let's take a look at that. All right, so far we've seen the wave creating a wave and concussing with all the particles in front. We've seen it accelerate. We've seen it split. Now, let's look at this, which shows everything in one shot. All right, now, this is what Fermilab has seen, and they claim are the smallest particles that exist, and I agree. And they claim this is a fixed, I agree, it never changes particle size or density, and it can't split. That's the tiniest it'll ever get. And it stays that same size as like a bowling ball. This one can get big and small. See it down here? It can get fluffy and bigger and smaller. This is the one that I showed you absorbs as it's going forward and gets real puffy, and then it'll spin, and the one that's unabsorbed goes to the top. That's all that is top spin and bottom spin in their lingo of all their particle zoo, they call it. So what we have seen here is these two particles together. These are neutrinos. The muon neutrino, electron neutrino. And here they are right down here. I will show you uno momento. Together, one of these, a black and a red or green or blue or whatever it is, but it's always going to be black, never change to black. These can change in colors, depends upon their intensity of spin. That's the color spin. Now, one set is what we've always called an electron. Back to back, two electrons, because these electrons are dipoles now. Don't forget, there's no more a negative electron, big positive core. No, everything's a dipole. The core of the nucleus is a dipole, and electrons are dipoles. And the nucleus is made of electrons. The nucleuses of all atoms are made of these particles right here, which are these particles. In their smallest configuration, we can split them into nothingness, one side and the other. But normally they're going to be either electrons flowing through wires or static or electricity, or even heat is basically excess electrons. When you put two of them together like this and shoot them through the air, that's light. So let's look at that setup here. All right, so we know these two particles are the ones we're looking for, and there they are. No question whatsoever, that's the black and the white. And the leading one concusses with the particles that are in front of it. You see the particles that are in front of it there? That one's going to concuss with those particles and glow. The other one is taking less, it's not impacting. The black just is along for the ride. The black is just a carrier. And it's dark matter and it's gravity. It will always want to be touching a white one. And the white one will always want to be touching a black one. The only way you can split them is the way we did it through the Venturi, or like that atom smashers they use. So what did we do? We created a sterile muon. The black one is all by itself now. And the white one turned into the shower. Exactly what it says. These are the muon, the neutrino, and electron neutrino. The black and the white together. And when they're together, they're neutrinos. All right? When they're together. Now these happen to be photons, but if you just took the two of them together, you'd have neutrinos. When they hit here as photons, they just scramble up into nothingness, which is they separate into the sterile muon and electron showers. So we have created these two separate particles and divided them. Boom and boom. Divided them apart. They're normally together. All right? And the particle accelerators, they hit them head on with protons, and they just smash everything everywhere. And they really have no real good information. It's just trash. Here's what they do. All right, here's what's going on. At CERN, Fermilab, and all the particle accelerators, they go around and around and around in circles, and bam, they hit these big protons together, which have all kinds of particles in them. They call them leptons and quarks and bosons and muons and taus, and they call it a particle zoo, because they don't understand everything just as pieces, and those pieces are these particles, the black and the white. It's the only thing that exists is the black one and the white one. And we can separate those. Just like they did at CERN and Fermilab, only they just got them in trash. We shoot them through our accelerator, which has luminosity coming out of your earlobes, and we actually create the two particles separated. Just exactly what they want to do at CERN. This is from Fermilab, that's not from me. And we did it, and we created so much energy there, so much luminosity, that obviously you can see it with a CMOS. They're just way behind at CERN and Fermilab. They're just way in behind. And now they're scared to move into this because it negates everything they've been doing. And it takes their equipment now is worthless. That's the problem. They just can't accept this kind of it's really just an upheaval in their world. That's the problem. And they're spending our money like water. This is government agencies. This is your money and my money. And they're doing nothing for society, nothing at all. Zero. I always end up going down that road because they won't let me talk. I've been trying to talk with CERN and Fermilab for years. I went to the University of Geneva. I showed them all this stuff. And then they reorganized their whole system, shut down CERN, and put on all new things, and now they're hitting head on. Oh boy, we're finding 10 times as many collisions. Well, that's because they're focusing on. We have 100% collisions. All they're doing is making the fields that surround this bang field to field, and then they're pushing all kind of particles to go flying everywhere. And really what they're hitting head on is, instead of big ball like this, they're hitting the balls like this. And when they hit balls like this, all of these particles go flying. Some of them go flying in this many chunks. Some of them go flying in this many chunks. Some of them go flying at me. And some, when they get real lucky, go flying in this many chunks, which is one. And then that is also a magnet, which has a black and a white. And that we have separated. They're just way behind. Okay, so where are we now? From the wave, which had the particle, to the particle accelerating, to the particle dividing, to showing what CERN and all of them want to see for particles. We showed them. Now, can I show the development of that particle? Can I show the things that they talk about, the tau neutrinos and the muons and the electron neutrinos and the Higgs fields? Yes, I absolutely can. Let's start with the development of the photons and the acceleration of the light. And here it is, right up here. All right, now, they're going to show, and I'm going to show you, and they talk about a tau neutrino. There it is right there. A tau has two blacks and one white. A photon has two blacks and two whites. An electron neutrino and a muon neutrino is a black and a white together. They call that a gluon. We separated the gluon into its sterile muon and the electron showers here. So not only have we seen a tau, we've seen the photon, and here we see that it splits everything into lots of bits and pieces. Now the same thing happens with the green. Let me show you the tau, the photon, and then the split there. Okay, so where are we now? Wave, particle, split, highlighted, development of the particle. Now let's see if the green holds the same characteristics as the red. And guess what? There it is. It does exactly the same. Identical. No difference whatsoever. Now, can we see the tau? We absolutely can. There's the two blacks and the white. Now see, the white is really kind of glowy in the middle of these two blacks. Green is very powerful, and the powerful part is the white part. But it's got the same structure, and the same black never changes. The white is the power part. Now look at here. It's just getting ready to spin. Remember I said the forward leading one charges up? That's the one that's charged up. That one is going to spin and come to the front, and that one will go to the back and discharge. And they just keep flopping. These are both in the front. It's the same particle. And I believe it's the same particle back here, manifesting itself as it goes forward. And they always stick straight up against the Earth. That's why they have upspin and downspin. And it's all polarity towards the Earth, because the Earth is the dark matter. The Earth sucks the white particles down. That's why static, lightning, electricity, right to ground. Gravity is the black. I don't know, I came back and looked, and the red doesn't look too much less powerful in the center. The center looks like it has a pretty good central power pack. Alright, so now we're going to start getting into the theory here. You have seen the particles, you've seen them. CERN says the same particles I'm showing you are the ones that they've been looking for, only they're trying to stay with their old equipment. They got to just stop it. Just stop. Just stop. Now, what happens after they come through the accelerator? These are Higgs fields. These are the other things that they look for, is the Higgs fields. Well, let's see what we got here. There's the wave. Let me open this up a smidge so it looks a little bigger. Now, here's what we got. You saw the wave. You saw the acceleration. This is coming out this way and coming straight at us. These are the Higgs fields. You see them? The Higgs fields, they're coming out of that accelerator. And what's happening here is at the very tip, they're recombining. See, they're solid white here, 100% white. And then when they smash into the blacks roll right into the white. Look at that. These are the tips of these fields. You see the black and the white is all reattached now? It's starting to reattach. Back here they're not catching up yet. They're still behind, and they'll catch up to the tips, and they'll turn black. Some of them are a little in the back there. A few of them here and there are already grabbing some black. But primarily it's the very tip of the wave. Well, Higgs field, which is a wave, which is a particle. So these are the Higgs fields. Now, I've shown you the wave. I've shown you the particle that was in the wave. I've shown you it accelerates. I've shown you it divides. I've shown you luminosity coming out of your earlobes. I've shown the Higgs fields. I've shown the reattachment of the black to the white. I've shown the particles manifesting, going from the tau neutrinos to the photons to the separate particles. And we started with light, and now CERN and all of them are going to try to do the same thing we're doing. But we've already done it, so I deserve a seat at the table. I deserve to speak. And they won't allow me to speak at Fermilab. I've been told not to contact them again because I am not a professional. Well, at this point, I am much more professional than Fermilab, way more. To be in that scientific realm and refuse to do science, that's, I don't know how you look at it, but I see it as a disgrace. I mean, what can they say? And I've been fighting them for 7 years now. I've had this all done 7 years ago. Okay, I'm sorry to get like that, but we could have free energy tomorrow. I'm almost certain of it. And I have shown this 1,000,000 times, and not a single response from the government agencies or anybody that does this stuff. These laser, you saw it accelerate. Look at that. That's luminosity coming out of your earlobes. Luminosity is power. P equals I times Z. Power, which is power is what we want. I is the number of electrons. We maybe not going to increase the number of electrons. Who cares? The energy is the luminosity. The higher the luminosity, the higher the power. So P equals I times E. If the E goes up 100 times, the power goes up 100 times. That went up at least 100 times. So we have increased power. We should be able to get free energy harvested within weeks. All of this stuff is on the shelf. It exists today. I've been refused to be a part of the solution, which upsets me tremendously. Now, every day they come out with a new particle and a new idea and a new graph, and this is the latest. All right, these are all their particles. Well, all of that stuff up here means nothing. The only two particles that exist are these two right here. That's it. That's the only thing that exists in our universe. You add them together and they start to make all the rest of these things. Now, I will show you my interpretation of this because I've done all of the little details that show what all of these things really are. And they all consist of these two particles right here. There's nothing other than that. And that's exactly what CERN says. I mean, Fermilab. Well, both of them. Here's Fermilab right here. And this is Don Lincoln. I went back and forth with him a bunch of times, and he finally just said, get lost. And very upsetting. Now, the field of particle physics full of what can be confusing dichotomies, fermion, boson, hadron, lepton, paper versus plastic, very cute, Don. You can add yet another to the list, extended and point particles. Well, these are the only two particles that exist. And he agrees that these are the smallest particles that they can find. And he says that one of them is the fixed size, the black one, and the other one is a point particle, which could be a zero size, has no mass at all. And I could agree it has almost no mass. But that's his interpretation. And I emailed, and I did this, and this is a sore subject, so I'm going to let this one fall for right now. But he also talks about quantum foam, which I agree. Empty space isn't empty. It's filled with the particles of light that I just showed you. And then he goes on to say this is the most successful theory ever. No, it's not. It's not successful at all. It's completely wrong. The core of every particle there is a dipole. We can separate them. As I showed you, we can create the W and the Z on their own, which is the muon and the electron flood, the electron shower. But these two make up the photon, they make up the gluon, they make up protons, they make up neutrons, they make up atomic masses. And it's much more complex than was thought before, because a proton is not one big ball. It's 1,836 of these two particles added together, which is the Z and the W bosons attached together. 1,836 of them makes one proton. Now, I have all this pretty well documented. Nobody knows how to get a starting point, because they don't understand any of this. So whatever they say, I am not going to count, but I'm going to show you what they do say. Okay, so where are we now? I just showed you what the current model is now, and they have the Higgs boson in the center, and it appears to me they think the Higgs is the God particle that creates all the other particles. It's not that way at all. Now, this is here's my simple model. Let's just start with this. This all exists. This is the whole new model. This is the whole new physics. It's the new model, electron flood theory, which is dipoles. It solves 100% everything, 100%. If you could come to me with any interaction in nature of any sort, I can explain it with this. The electron, we always thought was an electron, consists of an electron and a muon neutrino, the two of them together. So the dark matter nobody's ever seen before, because it doesn't radiate. The only way we can see it is because it gets in the way of our luminosity. Photon is nothing more than two of these electrons, which are dipoles, added together back to back like magnets. Now, I had 1839. It's not 1839, it's 1836. This goes back, 10 years ago almost. But all protons are electrons, the glowy part, the electron neutrino part, and then the black part goes to the center. Because all the white ones want to get away from each other. So they always go to the out. The blacks could go right on top of each other, couldn't care less. That's what's going on there. So all balls are, all particles are made of this. All right, we're made of that. This is nothing more than a dipole. It's a magnetic little particle. Now, when you take those electrons, which is this, and you add two of them together, like that, now you have a photon. And it looks just like this. And it tumbles coming through the air because of its polarity bashing into other particles that are in the air. I've talked about that. The wave creates a push against all those other particles, so you end up with a floppy little photon. When you add enough photons together, you get to a proton. Like I say, 1835 really is a proton, because it's the number of particles, and 1835 means they're not neutral. 1836 is a neutron. 1835 is a proton. And it just means that it wants one more electron, the proton, so it has one more that wants to get in. All right? A neutron has 1836, and it says, I don't want one, and I don't want to give one up. I'm good. I'm neutral. That's fine. But it's not one big ball like this of just things that can all break apart into like garbage. And that's all they're getting now at CERN and Fermi. They're just wasting all of our money and time. I'm sorry to keep going there, but there is nowhere else to go. Okay, so where are we now? We have seen Roger's very simple model. It's as simple as it. That's it. No more all this nonsense. And I've done all the nonsense. I'm going to have to show you my papers, because I've done all this stuff. I've done as deep as anybody's ever been into physics. And it just doesn't make any sense. It never did, and it never will, because it's all dipoles. Now, this is my model right here, and I'm just working on it, so I'm sort of drawing things in. But this is a picture of some of the things I'm doing in my journal. And I get to a point where I organize it eventually, maybe. Hold on. Okay, let me just quickly show you the blue, because this can show, you saw it speeding up here. I mean, there's very little question about that. And this is the blue slowing down. It's coming in real hot from the left, and then you can see it's almost straight, and then it starts to spin slower and slower. It spins to the left. I mean, it's spinning actually to the right, and the picture is drifting to the left. You have to understand, this is all one particle. Now, here it looks just like one little tiny glow. But here you can tell there's the both sides of the photon. Because this is a blue photon. Very, very hard to work with the blue compared to the red and the green. And the green, well, here, let me show you something else. All right, you saw the red particles separating out, and you've seen the green particles separating out. Here's the red and the green together going through the venturi at the same time. You see how the red just gets pushed out of the way and it barrel rolls. Remember I told you they're supposed to only spin this way. These are spinning this way. That never happens. Even the green is doing it. And so some red get tangled up in there. I don't know how that happened. But then the green reconcusses way out here. Now, so this is the two types of, it's just an increase in energy, and I believe it's the speed of the spin that creates the increased power. It's like if you spin something real hard and slap somebody with it, a ball on the end of a string, and it's going to hurt them. If it's just going sort of easy, it's going to bump off them. But if it's really going, you're going to get hurt. And that's just what this is, spinning. The speed of the spin, really, I believe. So now this just shows you that we can also separate the black from the white in green. But green is much more intense, much more powerful, as I just showed you. Now this is back from 2015, and I contacted the Russians about this. I said, you're showing exactly what we're showing with our light experiments, that the black can be separated from the white. Now how did they do this? They had a vacuum chamber out there, no particles in here whatsoever, nothing. and it's in zero gravity, so there's nothing being pulled up or down, because all of these white particles, they are going to go right to the Earth, because those are electron particles, just like lightning, static, electricity, right to ground. There's no ground. There's no ground out here. So what happens? Those particles float around. They want to stay away from each other and push all the black to the center, creating a black hole. That's a black hole in space. So I got a hold of the Russians. And the crazy thing is, when I was doing this, I figured, well, Fermilab's looking for these same particles. Don Lincoln just did this article on the black and the white, or the black and the red particle, called point particles. I showed you that right here. And this is from 2015 as well. Actually, it's 2013. So I had already known about these particles. And when I saw the Russians had separated them, and we separated them, I figured, well, I'll put Don in on this. And I actually copied him in with the Russians. And he sort of didn't work out too well. But I did continue to say, Don, this is what's the problem? And all he could say was, how did you photograph these? And I said, we use smartphones. And then it really went downhill from there. But as I showed you, CMOS is the way they're doing it. And they're the ones now that are upgrading to CMOS. And they call it a major upgrade. Where they'd like to be is where we were 7 years ago, CMOS. They had all kind of different sensors there that would destroy their readings, basically, because they were picking up on energies, but sucking the energies at the same time. Now they're trying, oh boy, we're really doing great with the high luminosity. We could do it with cell phones. Okay, I know this is running real long, but this is not something you can glass over in 2 minutes. So I showed you all the particles, I showed you the light, I showed you accelerating, slowing down, splitting, dividing, the muons reattaching to the electron glow, becoming particles again. I showed them separating from the fission and fusion. I mean, all of that is visually seen. No theory about, well, you had to conform to this, and standard model, if you know, you're way off because you're not using the standard model. Standard model doesn't work. Here's the one that does work, and this is my model right here. First of all, I showed you that's all there is those two particles. Now, I am going to show you my model against their model, because this is their model. Now, my model is on top of their model, because it is on top of their model, way on top. Okay, this you may think is a little geeky, but it really isn't. It's very, very, very simple. As I told you, the only two particles that exist are the W and Z bosons. That's it, those two. Everything else is constructed of those two. Now, the W boson, however, can be green or blue or red or any, I believe, just about any color. And the color speed, the speed of the spin indicates what color it is. The fastest speed is way up at the blue end. The slower speed is at the red end. Now, the Z never changes. Fixed particle, exactly what CERN and Fermilab say. No argument there whatsoever. Now, these two really are the muon and electron neutrinos. So the muon is the black one. They call it a Z boson or muon. And now we actually created sterile muons by separating them from the electron neutrinos. They are normally attached. They're black and the red, or the black and the green, the black and the blue. It doesn't matter. They're normally attached as a pair. Just like this. Normally they're attached. And they're up and down. All right? That's a down spin and that's up spin, however you want to do it. Now, what are my claims? I'm going to home in on this a little closer. This is their particle, how they see the universe. Well, here's how I see the universe. The red particle and the black particle. The red can be any one of these colors. So just red, blue, green, doesn't matter. It's just the intensity of the power. They're always going to be paired up when they're in their normal state. Now, they talk about the tau neutrino. I showed you what that is. It's a black with one of these colors in the middle and another black on the bottom, and it has a certain weight that's heavier. They know some of this stuff. They're not really far off. And then they go into the muon, which is really just a Z boson. It's the same particle. They don't realize it. The electron is nothing more than a gluon. Exact same thing. It's just these two particles attached together. No difference whatsoever. The neutrino, tau, is the same as the tau neutrino. These two are the same. This one is the same as the Z boson. This one is the same as this one, only it can spray, as I showed you, and it can be just red ball attached, or it could spray when it's impacting. And the photon is nothing more than two of the gluons, which are electrons, attached together back to back. And then when you get into your big particles, it's a ton of these. There's a ton of these altogether. The Higgs, as I showed you, is the recombination of these two after they're separated. This doesn't make these particles. This is when these two come back together. When we put them through the Venturi, you saw the black went around as a sterile muon, the white showered through, and then when they came back together, the black was right in the center and the white surrounded it. That's what a Higgs is the combination back together. So they got some thinking to do, and discussing. We got some discussing to do. Let's think about it that way. I'm not saying I'm right about everything. I could be totally wrong about, maybe 1% of what I'm saying. Anyway, what do I want to know? I want to know what the mass is, what the energy values are. Now, they come up with all this gigavolt energies, which I believe there are some enormous energies. The luminosity is incredible, and that is power. Luminosity is power. So I come through and I'm talking about the fixed, and I believe that fixed black particle is dark matter. It's cold, it's hard, it's gravity, and it's the heaviest part of these two particles. This one here weighs almost nothing, and I could show you this in atomic bomb blast, as I will. Anyway, I go through all this stuff about muons are glued to electron neutrinos and they exist as dipoles. I'm sort of working out my little things here and there, and about what heat really is and cold really is, and what superconductivity. Superconductivity means you just don't have any excess electrons whatsoever. So when that's cold. Cold means you suck all the electrons out. And then when you put electrons in, they just, zip, I can go anywhere I want. There's nobody waiting for me. Zip, no resistance. Zip, and instantly you start building resistance. That's why they have to keep it at that low temperature, but all you're doing is pulling electrons out. It's a no-win solution. However, what I'm showing is I think we can get free energy. I showed it. I showed you the little device. If somebody could try it and see, and all they'd have to do, because I don't know, I don't have the equipment to test this stuff, but all you'd have to do is see the power I'm putting in. If I could harvest that here, would I have more power than I used to put it in? If I did, whatever's excess is free energy. Free energy is something we really, really need, and this is not dangerous. It's not harmful to anything. All it does is squirt out extra showers of electrons. That's what you need to do. Electricity is showers of electrons, not just one. You need showers. And that's what that device does, that little Venturi. All right, thank you. All right, one last time before I give you the details. These are the particles we have found. We actually discovered them in light research using CMOS, complementary metal oxide silicates. And the CMOS absorbs these radiant luminosity. CERN and Fermilab are just starting to catch up. I'm not kidding you. It's unbelievable, but it's true. Okay, here's somebody I'd love to speak to too, is Michelle Starr. They're saying they finally know how black holes emit the most brilliant light in the universe. This is from today. Now, I can tell you how they do it, and it is what they're saying. It's from the bump. And they're saying down here, as the shock wave crosses the region, the magnetic field gets stronger because it's pushing against the particles that are just laying out there, so it gets stronger. And the energy of the particle gets higher. Yes, it starts to glow. The energy comes from the motion energy of the material making the shock wave. Yes, it's the particle making that field because it's concussing with all the other particles out there. It's not clear what creates the shocks. Well, the shocks are because they start bumping, pushing back and pushing ahead. It's push to show, push to show, push to show. And that is what creates these magnetic fields. One possible mechanism is faster material catching up to the slower moving clumps. Exactly right. Resulting in collisions. Exactly right. Further research could help confirm. I confirmed it already. Alright, this isn't bragging, it's just true. This is what I did. I love doing this stuff. And I did all of the calculations of how heat moves and different ionic solutions. And I always found out it turned into electricity. All of these different calculations that ended up being electrical power. All energy is electrical power. And all particles are dipoles. This is from some of my just general research, basically, and, all atomic stuff I did. And I came down to the point where, here it is right here, there's two types of energies, dipole to dipole, and there's polar and nonpolar molecules, but they're always dipole to dipole interactions. You can't have a positive core and a negative standalone particle. They just collapse. It never made any sense. It's totally wrong. Rutherford's atom was wrong. Transfer of energy from light is to atomic vapor. It's just little plus and minus dipoles. And I did all this stuff. It's not like I shortcutted and said, that's the end of it, I'm not going to listen anymore. I said, okay, you show me. Because I took a course, and I got an A in it, but I was at odds with the whole thing. I said, no, this is not right. None of this stuff is right, but I said, I'll do it. I'll do what you tell me, and then I'll show you what I have. And when I did, I just got destroyed. But I did all the stuff they wanted. I did it all. This wasn't a 15-minute job, and I did it to depths that nobody else was doing. All right, it's just as I'm doing now. And this is my model right now. So that's not bragging, it's just true.